Good morning, class. After yesterday's lecture, I was thinking how I can make sure we all learn this shape function topic very well. First, I decided to design a question for you to apply all the aspects of shape function. And then I said, let's create a video for reviewing the whole session. It will be much more useful later. You can watch several times and it can be much better. Okay, so what we talked, it was about shape function. Let me write shape function. For shape functions, we need to know two important terms. The first one was discritization, and the second one was interpolation. Okay, let's see what is the meaning of discritization. When we are using finite element method for a continuous model, usually we approximate that continuous model using information of a finite number of discrete locations. This procedure we call discritization. So we convert that continuous model to discretize several pieces. And then after discretization, we want to know what is happening inside each of those elements, and we need to interpolate to the using shape function. So we are going to use shape function to interpolate data inside each element. Okay, now we understand those two terms. Let's go and draw an imaginary bar. It's going to be like this. Okay. And area of this bar is a function of x, and x is going to be starting from here. The first thing I said, I can't investigate this one. So using the finite element method, the first step is going to be discretization. So let's discretize. And we said discretizing means we are going to cut that continuous model to some smaller pieces. Let's cut, for example, this one. Okay, for that piece, let me draw these dots to be able to show the distance from origin. So for the left side, the distance is going to be x1, and for the right side is going to be x2. And this x is our global coordinate. Okay, for this sample, I'm going to define shape function for this element in order to linearly interpolate displacement. So in this case, I'm going to define a linear shape function. But it is difficult for me because here I have like this element, the yellow one. I could have an element here. As you can see, this one is much bigger than the yellow one. So I should be able to define shape function in such a way that I can use this element, this shape function for any size of element. So let me write it down. Shape function should be defined in a way that I can use it for any size of element. So this is very important. How I can define a shape function to be able to use that shape function for any size of element. That is why we say, let's define a normalized length. Normalized length is going to be from -1 to 1 for any element size. What I mean, let's zoom it here. I need to have, this is my left side of element, right side of the left node, right node. And I need to define this element in a way to always have +1 for the right side and -1 for the left side. So it is going to have origin at the center of element for any size of element. And this is called normalized element size. And we can also name this normalized element size as a local coordinate system. So this is local coordinate system. So now we really understand why I need to have local coordinate system. Because the shape function should be able to apply for any size of mesh, any size of element. Some elements are larger than the others, like the yellow one and blue one here. So if all the elements have -1 for one side, +1 to other side, we can easily apply our shape function for this normalized lengths. Okay. So now we understand why we need local coordinate system. This local coordinate system, we call it psi, and it's going to be 2 over x2 minus x1, x minus x1 minus 1. And you know x1 and x2 is the left side and right side coordinate in global coordinate system. and psi is our local or normalized coordinate system. Okay, for linear case, the shape functions are going to be 2 points, 2 formulas. I'm going to call those shape functions n1 and n2. Why? Because for this linear case, I just have 2 points or 2 nodes for left side and right side. So left side is going to be 1 minus psi divided by 2. For n2, which is for right side, it is going to be 1 plus psi divided by 2. And to have a better understanding of these two functions, shape functions, I'm going to draw n1 and psi graph. Let's put the numbers. This is going to be number 1 here. This is half, and let me extend this one. I don't know why these axes, they have different size of unit scales. Yeah, okay, good enough. So for n1, it is going to start from left side, and left side eta psi is -1, and if I put inside n1 formula, it is going to be 1. So it is going to be 1 here, and if I put psi 1 for right side, it is going to be 0. Let's draw a line between those 2 points. Yep. What about the other one? Let's see. If I draw psi and n2 shape function graph, let's put the values here. 1, -1, 1, and this is going to be half. And if I draw this one, I put -1 for psi inside n2 formula, it is going to be 0. Let's go for red color. Draw line. Not drawing that. Let's go. So 0 here. If I put psi number 1 inside n2 format, it's going to be 1. So it is going to be here. Now I can draw the line. And it is passing that half. Okay. Let's write the final formula for displacement. If I want to find displacement inside any point of this element, so u, which is displacement inside that element, is going to be n1 times u1, which is displacement of the left side, plus n2 times u2. u2 is the displacement of the right side point, which we call nodes. Let me make sure it is clear. U1 displacement or deformation at left node displacement at right node. So those U1 and U2 are just numbers, and in 1 and 2 are linear shape functions, which I'm going to show you how we can design and find them. So using this formula, I can find displacement inside any point inside this element. So let's draw the graph for U. This is my psi or local coordinate. This one is U or displacement. And because it is local coordinate, it should start from -1 to 1 because we normalized it. For -1, displacement is given. Let's find, for example, this point, and we know it is a number U1. For right node, we have other displacement. For example, U2. So U2 and U1 are the point displacement for left and right side node, which we should have it. Usually it's unknown. Later we are going to find it, and then after finding we can interpolate any point inside. And now we can, using this formula, using why it is jumping, I don't know. Okay, so using this formula, I can find displacement inside that normalized element. And then I said that we prefer to use matrix form, which is U displacement is equal matrix n times, not like this, let me delete this part. So this is going to be n1, n2, u1, u2. Or even I can simplify this. For that u left side, I can use capital U to differentiate this u with the local values for nodes, and for n matrix just writing n. For this vector, small u. Small u shows these are the local displacement for the left and right sides at the ends, or depends on the, for this case, at the ends. If we had more points, for those points we already selected. Okay, so up to here everything is clear. Let's see all the material presented. Then I said